Well, it's 3 minutes after 1, and I'm the only show in the house, all by myself, which never stopped me from talking before. I just talked to myself for a while. But for students who viewing this video later, I should say a word about take a look at the schedule. Today would have been exam 2 on chapter 12, which is kinetics. And we also had a lab due last week. Lab number 1 was due. Lab number 2 on kinetics is due next Friday. So today, I'm going to talk about chemical equilibrium. Actually, just occurred to me that this is wrong. That should be 15. All right, so chemical equilibrium in my New River textbook is chapter 13. Those the PowerPoint slides are based upon that. Chapter 15 is in your textbook, Brown. Covers the topics that we're going to look at today. And chemical equilibrium. All right, so we'll get started. And I'll keep the roster open in case somebody shows up. I can give them credit for being here. All right. So let me share the PowerPoints and we'll get this ball rolling. And slideshow. Okay. So what we have here, I don't know if it's crossed your mind, but you may wonder, after we get into chemical equilibrium, why we did chemical kinetics first. Because kinetics is a much more difficult subject than equilibrium. And the reason is simple. Equilibrium is an expression of chemical kinetics in balance. And I'll explain that as we go. So, as you conduct a reaction, the reaction is proceeding, the reactants are becoming products, like this. But the fact of the matter is, they may be becoming products at a given rate that we've studied in the last chapter. But when you start to build up a concentration of C and D products on this side, you can also have a return reaction. Start going the other direction. And equilibrium is an expression of a balance between the forward and the reverse reaction. And by that I mean the speed at which the forward reaction occurs is balanced and equal to the speed of the reverse reaction. When that happens, you have equilibrium. And what that means in the macroscopic world, in what we can see, observe, and measure, it appears as if the reaction is static. In other words, you're not producing any more products, you're not losing any more reactants. Things seem to be fixed, one position. When in fact, on the microscopic level, the reaction rate, forward and reverse, are happening at some furious pace. The thing is, they're balanced one another. All right, so equilibrium in that respect is a dynamic process. So this is what it would look like for, say, nitrogen gas combining with hydrogen gas to make ammonia. You would obviously, at the very beginning, you would start off with no ammonia. That's a product. When you first start, you have nothing but nitrogen and hydrogen. So you have hydrogen here, nitrogen there, and you have 3 times as much hydrogen as you do nitrogen in a stoichiometric reaction where everything is balanced. You have just the right amount of nitrogen, just the right amount of hydrogen at the very beginning. Then as the reaction proceeds, you lose reactants, hydrogen and nitrogen, and you produce ammonia. And the ammonia is in the ratio of 2 ammonia molecules for every nitrogen and 2 ammonia molecules for every 3 hydrogens. So that's why the ammonia looks like it's right here, where this would be 1, the equivalent of 1 unit. This would be 2 units, and this would be 3 units. And when the amounts of each one appear to be equal, you also have an equilibrium. All right, this is another way of looking at it. The reverse rate is 0 at the beginning. Forward rate is probably as high as it's going to get. Before 0 order and a second order. First order, remember, well, first order does, actually 0 order doesn't depend on concentration. So 0 order would be a constant rate, no matter what the time and what the concentration. But first order and second order would have variable rates depending on the concentration. So you may start off here and the reaction rate would decrease over time as you deplete the reactant. Whereas the reverse rate would gradually increase as you generate products that are now reacting to return to the reactant side. And where they meet, those 2 reaction rates, where they meet, that's equilibrium. Okay. Now, of course, for this example, when you have a gas and a gas together, they've got to be in a confined space. If they're not confined, then you're introducing reactants from outside. We have to keep them confined. It's more difficult with gases than it is with liquids and solids. But in many respects, it's easier to study. So, in this example, we have water as a gas. Right? So the reaction is probably going to be over 100 degrees Celsius, as long as the atmospheric pressure hasn't changed, hasn't become greater than 1. And then carbon monoxide, when those 2 react in this closed vessel, they start to produce hydrogen and carbon dioxide. And eventually you get enough hydrogen carbon dioxide in the vessel that the reverse rate balances the forward rate. So what would happen if you were at equilibrium, right? You reached a certain concentration of reactants and products where the reaction is balanced. And then what would happen if you add more water to the system? Now, that concentration tends to require further reaction. So the water would react with whatever carbon monoxide was left until you reach an equilibrium balance again. What if we added hydrogen? That would tend to favor a reverse reaction. If you add more hydrogen, now you've got excess and you've unbalanced the reaction equilibrium by adding this component. And some of that is going to react with carbon dioxide until the balance is reestablished. So anytime you upset the balance, a system at equilibrium, if you do anything to it that upsets that balance, then it's going to respond in a way to mitigate some of that unbalance. And in fact, I just gave you Le Chatelier's principle. And that's what we're talking about here. Okay, what does the law of mass action mean? It's not obvious from the name what that means. But the law of mass action is an expression of equilibrium. And it was proposed by two Norwegians, Peter Weg, and his brother-in-law, Cato Goldberg, in the middle 19th century, 1864, as a matter of fact. The problem that they had set for themselves was trying to quantify the what they called in those days affinities, what drives the chemical reactions. And what they ended up doing was actually defining chemical equilibrium in mathematical terms. And what they did is just as valid today as it was then. It has held up over the decades, not quite centuries yet, century plus. They defined things that were happening in a chemical reaction in terms of those that imply motion and those that imply sitting still. The things that imply motion, what we've studied in the last chapter, reaction rates, they call dynamics. And in many respects, at least in physics, we refer to anything that requires movement of some kind, dynamics. They still use that term. And anything that is requires no motion, is roughly in balance, is called statics. But Weg and Goldberg use those terms to refer to chemical reactions. So reaction rate study would be dynamics, and equilibrium study would be statics. And they did all their work with solutions. So when they were discussing and defining the terms that were to be introduced into this law of mass action, they expressed the reactants and products in terms of concentrations in solution. So that would have meant molarity, moles per liter. And we still use that as the most common form of expression for concentration. Even if it's a gas, you can speak of concentration in terms of molarity. Although sometimes gas is more easily defined in terms of partial pressures. And that would have been covered in your first semester chemistry class. Okay, so this is what they came up with. So you have your reactants here. So you have a reactant A or a reactant B, and it has a coefficient, right? If there's no number there, then you assume it's 1. So each has coefficients, reactants, and products. And what they discovered was when you take the concentration of reactant to the power of its coefficient here, times any other reactant that's in that vessel with it, product. C is a product, D is a product. Concentration of this product to its power, coefficient, times the equilibrium concentration of this product to its coefficient power, that goes in the numerator as a product. And then in the denominator, you do the same thing with reactant A and reactant B. And when you express them in those terms, as long as the temperature has not changed, you can't mess with the temperature. Because if you do that, then we know now that you're altering the reaction rates. Right? You're changing the rate at which reactions occur forward and reverse, and that will change the equilibrium. So you have to maintain a constant temperature. And if you do that, then this expression, products over reactants, is equal to a constant value, a K. Now you can increase the concentration of C and D, and if you increase the concentration of A and B proportionally with their powers taken into account, then this ratio will always be the same. If you change just one of them, then the others are going to change to reestablish equilibrium with that K value. So when we change the concentration in that previous example, we add hydrogen to one side. Well, when you change that concentration, you no longer have equilibrium. But you can use what we understand about the law of mass action to reestablish equilibrium, and you can calculate the expected concentrations of all the other components in the reaction mixture. Okay, I'll point out one other thing. Notice that we have square brackets here around the concentration values for each of the products and the reactants. By convention, those square brackets mean equilibrium concentration. If you use parentheses instead, then you're implying that the reaction mixture is no longer at equilibrium. When you use square brackets, you're saying we are now at equilibrium. Or if you have an unknown in there, you're trying to determine equilibrium concentration. Okay? So I don't need to write that on the board because it's right there on the slide. One other thing that I will make mention of is the K value is usually reported without units of measure. And that really makes a lot of sense, because what could the units of measure be for that K? Sky is the limit. It depends on the reaction upon which K is based. Right? And with those powers introduced, we could have a whole mess of possible units. So the convention, and in any reference manual that you look up the K value for a reaction, you will see that there are no units reported. The K is assigned to a particular reaction. And if you treat the reaction with care and pay attention to the details, then the calculated values will be correct. All right. So maybe I better, for this discussion, I need to have something to work from. So let's say we do have this and this. There we go. And our equilibrium expression will be products over reactants Okay. Now, if we have to, for some reason, manipulate this value because of something we've done to the reaction. Let's say we want to study the reaction in the other direction. What does that do to the K? Say we want to reverse the reaction. Instead of starting out with A and B, we want to start out with C and D. Then what would the expression look like? If we have to do it this way, then what would our expression be? Then we would have a different K, of course. Let's say K1, this K2. Then we would have A on top to a power, and B. And then C on the bottom, and D. Okay? So if you know this reaction and it's given, but you want to study it in the other direction, all you have to do is say, now this K value is equal to the reciprocal. It would be like this. Or if you wanted K2, you want to study this reaction, you just say that's equal to the reciprocal of K1, right? Because we've just flipped it like that. Okay, very simple. Notice also that when we were writing this law of mass action, the coefficients do enter into the calculation, whereas when we were studying kinetics, we couldn't depend on the coefficients of the overall reaction to inform anything about the rate law. But now with the law of mass action, the coefficients are intimately involved with the calculation. Okay. So what happens if we multiply, if we have to multiply the equation by some factor? Say we have to go like this. Remember when we were balancing equations, when we used the fraction trick to get rid of the fraction, we multiply the whole thing through by something. Well, if we're using Hess's law that you learned in your first semester, where you're combining different reactions to get a target reaction, a final reaction, then you may have to manipulate them a certain way. Hess's law we used in terms of what's the enthalpy of the reaction, the final reaction, based on what you've done to the formula or the reaction here, then you would have an effect on the enthalpy, and then you would add them together. But now we're talking about equilibrium constants. So when you multiply by a factor, okay, you get a fresh marker. When you multiply by a factor, what does that do to the expression? Well, it says 2A, 2B, 2C, and 2D, right? So you would have a 2 times each one of these. Okay? Now, let's move this one out of the way. Now, what can we do? Well, remember the laws of exponents. This whole expression, if everything has a 2 multiplier in its exponent, then that's like the whole thing together like this. To that power. Okay? So the new K value is going to be the new K is the old K to that power. Okay? So if you have to multiply the equation through by a factor, then that factor becomes the power that you apply to the old K value to get the new one. All right. So this is just a reinforcement. As long as the temperature doesn't change, then the K is constant. And you can change reactants, products, concentrations, starting the reaction. But once it reaches equilibrium, then those equilibrium concentrations fit into the formula and give you exactly the same K as some other mixture would. So that brings up the topic of the difference between equilibrium constant and equilibrium position. All right, the constant is just that. It is constant for a temperature. But the equilibrium position is referencing the actual concentrations of reactants and products. So the equilibrium position could be different. If you start from a different concentration of reactants, you're going to end up at a different position than if you use, say, half of that. Okay, so the position is variable, but the constant is not. All right. Let me be sure I got my there. Notice that we have a number of different subscripts for the K value. And those are meant to help inform the reader under what conditions, or are there special conditions? Are we considering a certain type of reaction? If it's just a general equilibrium, we just subscript EQ for equilibrium, KEQ. That covers everything. But it does separate that K from some other K, like for our rate laws. It's a different K altogether. If we're talking about the dissociation of the water molecule, which it will do in water, water will do this. Right? That's a valid reaction. Then the KW is used for that reaction, and only that reaction. That's what KW means. Ka is referencing this dissociation of an acid in aqueous solution. So if we have something like this, and it's an aqueous solution, then it will dissociate into this and that. Actually, this is not a good example because the equilibrium here is so far to the right, it makes this 0, so that's infinity. So I probably should have used a different example. Let's say just generic. Say we have an acid here, and it's a weak acid, which means it only partially dissociates. Most of it is over here, but some of it's over here. Then we can write an equilibrium expression with this on top, that on the bottom, concentration, and the K associated with that expression, that rate law, excuse me, that mass action law would be Ka. We can also express solubility products. And we'll talk about those at some point in the future. But SP means solubility product, and it would be something like some partially soluble substance like calcium carbonate. Actually, calcium carbonate is a solid, but it can produce aqueous amounts of these. And you can write an equilibrium expression for that. So that would be the KSP. Some reactions stay in the same phase. So we use a KF, or K of formation. And we're going to do one of those experiments with using silver and ammonia. They have a K that's associated with the formation of the silver ion combined with ammonia in H3 in solution. All right. And then the other one that is widely used is the KP. P means pressure. So for a KP, all the reactants and products are gases. Well, I'll qualify that in just a second. But it references partial pressure. So it could be in atmospheres, it could be in pascals. So here's an example. Say we have, again, nitrogen combining with hydrogen to form ammonia. And we would write the expression as ammonia to the second power, the partial pressure of ammonia, right? Remember Dalton's law. The total pressure is the combined pressure of that gas, and that gas. But the partial pressure of ammonia is a certain value squared, divided by the sum, the product of the reactants. Nitrogen gas to the first power, hydrogen gas to the third power. Right? That could also be written. Now, when we write it this way, I said earlier, this is a non-equilibrium situation when there's P involved. In fact, very often the parentheses are omitted. You just say P like that to the second power. Without the parentheses. You could also express this reaction in terms of molar concentration. In H3, square brackets to the second power. Those K's will not be the same value because these are different units. Right? But they are related. And we can devise or derive a formula that will convert one into the other. So continuing with partial pressures, if you have these values, right, these are equilibrium values at a given temperature, right, fractions of an atmosphere. Then you just plug them in the formula, like that. Don't forget your powers, right? And don't forget, once you get them in there, to use those in your calculation. Right? You got to square this one first, cube that one next, and then you can do divide and multiply. Right? Isn't that PEMDAS? Right? P for powers. No, P for parentheses, excuse me. P for parentheses, E for exponent. So you do everything inside the parentheses, and then you do the exponent. And then you do multiply, divide, add, subtract. And using partial pressures, we get this value. All right. If we want to convert from one to the other, this formula is appropriate. Right? So there's your concentration in molarity K value. There's your partial pressure K value. And if we multiply this K times this term raised to the n power, I have to explain what n means. This is a universal gas constant, right? So this one would have the atmospheres in it. And the temperature in Kelvin. Now, what does the delta N mean? The delta N means what's the change in moles of gas. So you sum the coefficients of the gaseous products and subtract the sum of the gaseous reactants. So back here, this would be 2 minus 4. So that delta N would be a minus number. It would be a negative number. If you plug those values in, let's see, are we going to do that? Yeah, we're going to do that. So here's your universal gas constant. Here's the temperature. Say it's at 35 degrees. This is 2 minus 4, which would be a minus 2. And then here's the actual K that we determined for partial pressure. Then we solve for this K, and this is in terms of molarity. But we don't report the units for obvious reasons. Okay, so notice that there are different values. Okay, what type of equilibrium can occur? Well, you can have an equilibrium in which all of the components are in the same phase. For instance, if they're all gases, then that's homogeneous equilibrium. If they're all aqueous solutions, that's a homogeneous equilibrium. So this hydrocyanic acid dissociates partially, not very much, but some, into hydrogen ions and cyanide ions in solution. And you can calculate a K value for either one. A heterogeneous equilibrium is one in which at least one of the components, reactants or products, is in a different phase from the others. In this case, you've got two solids and one gas. In this case, you have a liquid, and this is the dissociation of the water molecule. Excuse me, this is probably electrolysis of water. You're breaking water into hydrogen gas and oxygen gas. It's not the same as this one. That one. That's something else, differently. So, when you have a heterogeneous equilibrium, we apply a rule. And that rule is that all solids, any solids in the equilibrium, disappear. They are not part of the equilibrium expression. Why? Because their concentration doesn't change. A solid is a solid, right? And it's a solid until it disappears. No concentration change at all. So the solids are left out. Same thing for pure liquids. This liquid right here, water, it's not part of the expression. So what does that mean for the first one? Let me check my hard copy and see if I'm stealing my own thunder. Let me keep going with the slides. Right? I think it starts to flesh this out for us. Right? So the position of the equilibrium when it's a heterogeneous variety doesn't depend at all upon the pure solids or the pure liquids, because their concentrations do not change. So in this case, you have a solid here, and a gas there. The equilibrium expression only includes the gas. And that's by convention. So if you see that reported, for this reaction, you see the K reported in the literature, in a reference manual or somewhere else, then that K is derived only from the gas. Let's see. I didn't do the other one. How about this one? So if you have two water molecules that are liquid and they produce two hydrogens and one oxygen, how would we write that expression? That K, let's say for simplicity's sake, first we're going to use concentration. So the concentration of hydrogen to the second power times oxygen to the first power. And water's not there. Or if we wanted to do it this way, we would have, partial pressure of hydrogen squared times the partial pressure of oxygen to the first power. Okay? And pure liquids are not included. All right. So we can use the K value to give us some indication as to which side of the reaction is actually favored. For a K value that's much, much larger than 1, the reason we don't say it's just purely greater than 1 is because those powers interfere with that approximation. But if the K is very, very large, greater than 1, then the equilibrium will predominantly exist in the product side. You have mostly products. Equilibrium lies to the right. And when we say lies to the right, you need to be referencing an equation. Since we said that the K is much larger than 1, we know that we're talking about a reaction that's going this way, and we're on the right-hand side, predominantly. So that reaction position is toward the products. If it's much, much, much less than 1, like 10 to the minus 5 or 10 to the minus 6, something like that, then we know that we're favored to the left because of the way the fraction is written, right? Products over reactants. So if products is the majority, you're going to have a number larger than 1. If the reactants are majority, you're going to have a fraction that's less than 1. So that's a qualitative or semi-quantitative deduction drawn from the K value alone. So if the equilibrium lies to the right, the value of K should be large, greater than 1. And if it's small, it should be smaller than 1, much less than 1. All right. So most reactions have to start somewhere, right? And under those circumstances, they're not at equilibrium yet. But what we can do is use that law of mass action to make a prediction. Which direction will the reaction proceed? To the right or to the left? And we calculate not a K value, but a non-equilibrium value called the Q, or the reaction quotient. And that makes sense, right? Because the law of mass action is a quotient. Products over reactants. So we calculate this Q value using the same expression as the equilibrium, only now we put everything in parentheses instead of square brackets. Okay, that's our Q value. All right, so what does that tell us about the reaction? Well, obviously the easy one is if Q is equal to K, which is rare, then we're already at equilibrium. In other words, if we add reactants and products in a certain proportion and calculate the Q and it's equal to K, then the reaction is not going anywhere. It's going to sit right there because we put concentrations that calculate an equal Q to K. No shift will occur. If Q is greater than K, what does that say? I better write the reaction here. Okay. If Q is greater than K, what does that say? Well, the equilibrium would be a certain arrangement here. If Q is greater than K, what's the proportion of products to reactants? That says that the reactants are too high. Excuse me, the products are too high and the reactants are too low if Q is greater than K. Right? Let me say that again. If this calculation is greater than K, that means that this value is too high and this value is too low. So which direction will the reaction proceed? Back toward reactants, from products to reactants. So the system will shift to the left, the way it's written here. Consuming products to make more reactants until equilibrium is reached. Okay? Reverse that situation. Say Q is less than K. If Q is less than K, that means that the products are too small and the reactants are too large. So now the reaction is going back toward products to the right. Okay? That's what Q helps us to do. Now, why would we want to know that? Because when we start trying to determine the end concentrations for a mixture that's not at equilibrium yet, we need to know which direction it's going to move. If we don't know that, then we can't do the calculation. So that's why Q is important. Now, there are some circumstances where you don't need Q, right? If you're starting a reaction with A and B, then you know it's going to the right. Or if you start with C and D, you know it's going to the left. No doubt about it. So under those circumstances in the last chapter, when we were studying kinetics with initial rates, we started off with reactants and no products. So we knew it was going to the right. So in that scenario, it fits. Well, it would obviously be make more of these. Q would be less than K. Okay. So let's do one of those calculations that I was mentioning earlier. So we're going to use this reaction. All right, let's scoot this back over. There we go. So in this case, we have an iron 3 ion in solution reacting with a thiocyanate ion, SCN-, to produce this soluble complex, iron 3 thiocyanate. Okay, the charges do balance, right? 3 plus and a 1 minus makes a 2 plus on this side, and the proportions are correct. The equilibrium constant for this reaction would be that one with the subscript F, the formation constant. All right, so we have our balanced equation. Now we're given initial concentrations. 6 molar iron and 10 molar thiocyanate. They're mixed together, and at equilibrium, we determine the concentration of thiocyanate complex, iron thiocyanate, to be 4 molar. What is the equilibrium constant? All right, that sounds like it's almost impossible, right? Well, there's a method that helps alleviate some of that stress and get you to the right answer. All right, so there's our beginning situation. There's our ending. Right, we know the ending, which makes it much simpler. All right, so what we do is we construct a table called the ICE table. And that stands for what are the initial conditions, what changes occur, and what's the equilibrium situation. Now in this case, since we know the final concentration of iron thiocyanate, every one of these places has a real number. But you can also use the ICE table with unknowns in place, you know, X's and Y's and that type of thing, to help you find out, to answer a question. So this ICE table is useful from now on, really. Even when we get into acids and bases, you'll be using the ICE tables. So get familiar with it. Now notice, the way I like to set it up is I have the balanced equation up here, and then underneath the terms that are important is the columns of our table, right? So this refers to iron 3 plus all the way down, thiocyanate all the way down, and the complex all the way down. So what are the initial conditions? Well, the initial conditions are 6 molar iron and 10 molar thiocyanate. Well, how much complex is there? 0. At the very beginning, there's nothing. Okay? So what change has to take place? Well, we know this concentration right here is going to be 4. That's given to us, 4 molar. So that means we had to add 4 molar to this side. That's why the plus 4. So what does that mean to the other side? Well, the ratios, because this is a balanced equation, the ratios are 1 to 1 to 1. So that means we had to lose 4 molar from this side and 4 molar from that. These two reactants had to lose concentration by 4 molarity in order to produce 4 molar on the product side. Right? So we subtract that from these. Now you've lost 4 molar from that 6 molar original, and you've lost 4 molar from that 10 molar original. So now the equilibrium gives us 2 molar iron, 6 molar thiocyanate, and 4 molar complex. Now that you know the equilibrium values, just plug it in your mass action equation. Product to the first power divided by reactant 3 plus and reactant thiocyanate, both of the first power. And our K value is 1/3, 0.333. Okay, that was a very simple problem where we use the ICE table. Now that we know the K value for that reaction, if one of these happens to be an unknown, we can solve for it, right? It's just like any equation. If there's only one unknown, you can solve for it. So here's the situation. Now we've changed the conditions to where we have 10 molar iron and 8 molar thiocyanate. The question for this one is, What's the concentration of the iron thiocyanate complex? Okay. Looks tough, doesn't it? Not really. Just follow the same method. Right? It looks a little different because I drew the table different. And I put the values up here, actually. That one should be superscripted. Let me make a note and I'll change that in my next iteration of this. There. Okay. So if the initial concentration of iron is 10, thiocyanate's 8, the complex is 0, right? What change has taken place? Well, which direction is the reaction moving? Because there's nothing over here in the product side, it has to go to the right. So that means you're going to lose some of iron and some of thiocyanate, right? So that's our unknown, X. We're losing X of iron, but they're 1-to-1. So we have to lose that same concentration of thiocyanate, right? So minus X and minus X there. Well, it's all 1-to-1. One of each on this side, one product. So that means what's going to show up over here is a plus X concentration for the iron thiocyanate ion. Now, what's the equilibrium situation? The equilibrium is going to be 10 minus that amount, and 8 minus that amount, and that amount total is X. So we plug those values into the equation, right? Product, and then 10 minus X, 8 minus X here is equal to the K value. Now, here comes the sticky part. Notice that when we solve this equation, we've got this term with X and this term with X. When you multiply them together, you're essentially expanding a quadratic. Remember that from algebra. You're expanding a quadratic equation. So that gives you an X term, an X squared term, an X term, and a C value in mathematical terms. So if we set that, if you want to solve a quadratic, then you have to have the quadratic on one side and a 0 on the other side of the equal sign. Then you can use the quadratic equation to solve it, right? Right. So this is minus b plus or minus the square root of b squared minus 4ac divided by 2 times a, 2a. That's the solution to your quadratic equation. And I think I still have, yeah, on the back of my calculator, I put that formula right here, just so I don't have to look it up. So if we solve that equation, right, because we have a plus and a minus here, you solve it one way with a plus and one way with a minus. So you get 2 answers. Then you have to decide which one of the answers is reasonable, right? If X is 15.99, is that reasonable? No, because if you start out with 10, how are you going to end up with 15.9 with a 1-to-1 relationship? Can't happen. So that's the one you throw out. And the one you keep is 5. So now the concentration of iron thiocyanate is 5 molar, right? If you want to find out what's left on the product side, just subtract 5 from it. 8 minus 5 is 3. 10 minus 5 is 5. So you have 5, 3, and 5 as your equilibrium concentrations. And if you want to confirm that your K value, that these values are correct, just plug them back into the formula, right? 5, 3, 5, and you should end up with 0.333. Okay? Now, there's a shortcut that can be used when the solution of a quadratic equation would be difficult. Now, when can we use the shortcut and when do we have to use the quadratic? Well, you look at the concentrations here, right? With this 5 in place, that 5 is a significant fraction in this 10 minus x, right? So we cannot assume, we cannot ignore the x. We have to include the x, which means you have to solve the quadratic. In some cases, if the x is extremely small compared to these other values, then you could ignore these two x's and just keep the 1. And in those cases where x is extremely small, then the approximation of x that you derive from this formula without using the quadratic, by the way, because it's a single x, is very close to the one that you would derive from the quadratic. And you can do both of them and satisfy yourself. That's an assumption that can be made in some cases when x is very small. All right, so if we do that same calculation with a different spread of concentrations to beginning, the initial concentrations, we get a different value, right? Instead of 5 now, we get 3 under these conditions. So we have a different equilibrium position, but the K has not changed. Okay, so here's what you do when you solve an equilibrium problem. You've got to have the balanced equation first. If you don't have a balanced equation, and that also means you got to write the reactants and products correctly. Right? So you got to write those correctly. You have to balance the equation. Then you write the equilibrium expression. Right? That's the easy part. Remembering that pure liquids and solids are not part of the expression. Which also means what? Pure liquids and solids are also not part of the ice table. Only the components that enter into the law of mass action, into that formula, those are the ones that enter the ice table. The rest of it don't. So you list the initial concentrations in your ice table, calculate the Q value to see which direction you're going, because you can't say anything about the change. Remember, initial, change, equilibrium. You can't say anything about the change until you know which direction the reaction's going. Is it going to add reactants or is it going to add products? Right? You have to know that. So if Q value is necessary, calculate it and see which direction you're going. Then you can move on down the table and input values and unknowns. Now, the choice of the unknown sometimes is critical, especially if you're time constrained, like during an exam. If you choose the x, the unknown, carefully, then when you solve for the x, you got your answer. If you don't choose the x carefully, then you have to also be careful at the end. Once you find the x, use it to calculate the answer. Okay. Sometimes you don't have a choice. But oftentimes, if you choose the x carefully, like in our previous example, right? Let's go back. We chose the x here because the x was going to actually give us the answer. Okay? Then, once you determine expressions for the equilibrium concentrations, they may have unknowns in them. Plug them into the law of mass action for that equation, for that reaction, and solve for the unknown. Then check to be sure that that value is valid, if it's correct. And to do that, you put in real values into the expression, calculate that, and compare it to the k. If it's not the same as the k, then you made a mistake somewhere. And it's better to know before you put the answer on an exam that you've made a mistake. Then at least you can correct it. Okay, so we've got these possibilities, and we could go through. I've got an hour to go, and let me see how much more. I've got a little more discussion to do. If we have time, we'll come back. But we know the k value. We know how to build the ICE table for each one of these scenarios, right? So you have a different scenario in each one. Now, in this case, right, we actually start off with a concentration of product. Right? So in that case, maybe I ought to do one of them. Let's do the first one. So I'm going to write my equation here. All right. So the initial concentrations are what? Well, the initial for iron is 9 molar. The initial for thiocyanate is 5 molar. And the initial for iron 3 thiocyanate is 1 molar. Okay? Change. Equilibrium. All right, which direction is that going to move? We don't know. We have to calculate the Q value. So we're going to write the expression over here for K is equal to this one divided by this one right? Then we plug in values. So this is our Q calculation. We have this one divided by, actually that's not a bracket, that's a parentheses, because we don't know that it's equilibrium yet. And then you have 9 times 5. So what's that value? 1 divided by 45. I think that's a little less than 3, don't you? 0.3, less than a third. So 1 enter 9 divide and 5 divide. So that's 2.22 times 10 to the minus 2. So in this case, Q is less than K. So if Q is less than K, that means we have not enough product and too much reactant. So we're going to move that way. So that means we're going to subtract from this side. By the way, what's the question? Find the equilibrium concentrations of all species. Okay, so we can pick our X anywhere. We got to calculate the others based on it anyhow. So let's say we minus an X here, minus an X here, plus X over here, because it's moving that direction, correct? Now we have 9 minus X, 5 minus X, and 1 plus X. Okay? Now what do you do? Well, we plug it into the equation. Which is now K. Let's see, I need to get one that's writing better. So the value for this one is 1 plus X. The value down here is 9 minus X and 5 minus X Okay. Oh, and that's equal to 0.333. Now, do we have an opportunity here to ignore x in this case? It's probably, with that size k, we're probably going to get a substantial amount of x. Right, so we're going to have to solve the quadratic. So this one is equal to 1 plus x divided by 9 times 5 is 45, and x squared, right? 2 minus x's make a plus x squared, and then 5 times x and 9 times x. So this will be a minus 5 and a minus 9, which is a minus 14x. So now, what we're going to do is, let's see, we have to put this one over on that side, right? 0.333 times 45 minus 14, and that's an x there, excuse me, x plus x squared is equal to 1 plus x. So I need my calculator for this one. All right. So 0.333, 45 times that is 14.99. And then that times minus 14 is minus 4.66. And then plus 0.333 x squared equals 1 plus x. All right? So now we want to get 0 on that side before we can use the quadratic. So we're going to take this x, which makes it a minus x, applied to, excuse me, that value. So we have a minus x, which makes, let's see, where am I going to write that? I'm going to have to erase some of this. So now I'm going to take this equation up here, and this 1 is going to be subtracted from that because it's positive this side, it'd be negative that side. So we have 13.99 minus, and this x is going to be a minus x, which is added to that minus x, which would be 5.66x, and then plus 0.333x squared equals 0. All right. Now we can solve for x. If we write this in standard form to use the quadratic equation, this is the a term, this is the b term, and this is the c term. All right? So I'm going to go through this thing in detail, just so that you can see it done. Let's see. I'm going to erase this part here. So what's the expression? Well, x is equal to minus b minus a minus 5.66 plus or minus the square root of, let's see, b squared, right, minus 5.66 squared, and minus 4 times a times 4ac. 0.3, oh, excuse me, wrong. B's right. A is this one, 0.333 AC, 13.99. Okay? Oh, all divided by 2A, I think. Yeah, 2 times A. A, 0.333. All right, so we're going to get 2 values, one where we do plus and one where we do minus. So that being the case, why don't we calculate what this is and sort of put it out here to the side. Then we can do the plus minus calculation. Need another marker. Okay, so what's this one going to be? 566 squared. And where is that? Here it is. Then we have this one. Before we can subtract it, we need to multiply those together. 0.333 and 13.99 times. So this one is 18.63 subtracted from that one. 13.40. So this term here is 13.40. So now we can do, this is a positive now. We can do that one. Oh, square root, excuse me. Square root of. Square root. Find it on my calculator. This is not my favorite one. Well, where is it? There it is. 3.66. Now, that's this term right here. So we can say x will either be 5.66, because that's it there, plus 3.66 divided by 2 times that, 0.666. So that one is 5.66 plus 13.99. Or 5.66 minus 3.66 divided by 0.666. I think this is going to be the one. Minus 3. All right. So we look back at our original concentrations, 9 and 5. How are you going to get 14 out of 9 when it's a 1-to-1 ratio? Won't happen. So that one is out. And that's your answer. Well, that's your answer for X, which was subtracted from both sides. All right, so that's not your answer. Sorry. We need to go back and say 9 minus X would be 6. 5 minus X would be 2. And 1 plus X would be 4. Right? So 6, 2, and 4 are the answers. Okay? So you can do that for both of those other examples. And the answers are given to you there so you can check your work. Right? That's what it should look like, and that's what it should look like. There's another way to do these calculations. And I'm not sure if I've got it in the slides or not. I'll check it just a second. It's called the method of successive approximations. And the short version is you do the calculation and you set up the equation in such a way that you have your x's in there. And then, in our case, for the bottom, where you have the x's down here in the bottom of the denominator, right? You have an x there and an x there. You get rid of those. You say, throw them out, and just keep the x up here, and do a calculation. And what does the x term look like then? It'll be wrong, but it'll get close. The next time through, you leave that x alone, and you put the first calculated x down here. Then you do the calculation again. And you check yourself. The first times, you don't need to check yourself because it's going to be wrong for sure. The second time you check yourself by putting the x value into the calculation and determining these values here. Put them into your equation and see if you get a k value of 0.33 in our case, 333. If you don't, then you take the new calculated x and go back and do it again. And you keep doing that until your approximation gives you very close to, if not exactly, the k value. That's why it's successive approximations. You keep doing the approximation with the new calculated x each time, and you get closer and closer and closer. With some laws of mass action, that's the only way to do it, because you may end up with an equation to solve that's not quadratic. Right? It could have powers of 3 or 4 or 5 or 6. In those cases, approximation is the only way to go. And these days, with the computing power we have, you can write a program that will do that in a split second. You don't have to do it by hand. The hard work is setting up the program. So I just wanted to give you that verbal description, and if we find ourselves without an example, then you at least have that knowledge. And some of the review problems that you'll find in the review document will lend themselves to using successive approximations. In fact, when I wrote out the solutions to the problems, I may have included successive approximation instead of the quadratic in some cases. I hope I did. I have to look, see. Okay. So let's say we have a 2 mole sample of ammonia introduced into a 1 liter container. So what's the concentration? 2 molar, right? 2 moles per liter. At a given temperature, the ammonia partially dissociates according to this equation, right? First of all, is it balanced? Right? 1 nitrogen, 2 nitrogen. No, it's not balanced. You have to balance it, right? So you got to balance that equation. And then the question is, at equilibrium, it says that 1 mole of ammonia remains, right? So we've used half of it. It's gone from 2 molar down to 1 molar at equilibrium. What's the K value? All right, so we balance that one. Oh, it's not going to go through the process. So what you have to do is balance the equation, then set up your ice table, right? If you're starting off with ammonia only, you know it's going to the right, right? So that should be simple, setting up the ice table. And it's similar to that earlier one that we did, right? You're going to have values all the way down. no x values. You're going to calculate k from this information. Let's see. All right, this is an example where the slides don't give it to us. I've got time. I need to take a restroom break. So what I'm going to do is, let's see. I'm not going to stop the share, and I'm not going to pause the video. I'm just going to let it keep recording, and when I process the video, I'll just cut this section out, so you won't have to sit there and watch empty space. Okay, I'm back. So let's do this one. All right, what are we given? 1 mole of N2O4 gas is placed in a 10-liter vessel. Right. So notice also that if you're given absolute amounts here and volume, you got to calculate the concentration before you can start, because it's all based on concentration. Now, when you get to the lab on silver and ammonia together, you're going to be setting up an ice table there, and I give you nauseating detail in the method itself. But for that example, it's more convenient to calculate changes in terms of absolute amounts first, and then convert everything to concentrations. So that is one exception where it works better to do it the other way. In this case, we're going to use concentration. We have to calculate it, right? So 1 mole placed in a 10-liter vessel would be 0.1 molar. The equilibrium equation is this. All right, and those are both gases. Okay. Now, it's allowed to reach equilibrium. First of all, is that balanced? 2 nitrogens, 4 oxygens, 2 times 2 is 4. It's balanced. Now we set up our ice table. So what's the initial concentration? This one is 0.1 molar. That one is 0. And it's allowed to reach equilibrium. So we know which direction it's going. It's going this way. Well, we need to write the law of mass action first. So K is given. Calculate the equilibrium concentration of each one. So K is given as 4 times 10 to the minus 4. Equals NO2 squared divided by N2O4 to the first power. Okay, now we know that's going to happen. We know we're going to add some over here. So why don't we just make that X? Well, if we make this X, why don't we make this 2X? And make this X. Because if this disappears at 1 mole, then this appears at 2 moles, right? Keeps everything whole numbers. We don't have to use fractions. Okay. So now the equilibrium situation is 0.100 minus X, and this one is plus 2X. Okay? So now we can plug that into our formula and find out what X is. 4 times 10 to the minus 4 equals this one squared over this one. Okay? Now, we have to make a decision. Do we want to do this quadratic, or do we want to use an approximation? Well, let's think about it. With this value of k, what does that say? That says that this value is going to be very small, right? Very small compared to anything that it's subtracted or added to. So as long as we only have one term that's squared, then we can take the square root. And we're good. We don't have to use the quadratic. Quadratic is only operates when you have an x squared and an x. But if you only have an x squared, then square root works every time. So let's say this is approximately equal to, go ahead and square this one, 4x squared divided by 0.1. Okay, see what I did? I eliminated that x. So now we solve. Right. So 0.1 times this is 4.00 times 10 to the minus fifth equals 4x squared. So take that 4 and put it over here. Now that equals to 1 times 10 to the minus 5 is equal to x squared. So x is equal to the square root of 1 times 10 to the minus 5. Okay? That's a whole lot easier to solve. 1 exponent 5 change sign enter square root. So 3.16 times 10 to the minus 3. That's what we calculated for this value. Now, the question is, was that a valid assumption? How do you check that? Well, we generally use the 5% rule. In other words, if we take this value and put it in that expression, well, not that expression, but if we say, all right, if this is the concentration of that, excuse me, we need 0.1 minus that value. Right? So the concentration of this one is going to be 0.1 minus 3.16 times 10 to the minus 3, right, because of this. And this one's going to be 2 times that value. So that's 2 times 3.16 times 10 to the minus 3. Okay, so we're going to get a value for that one, and we put it in here. And we get a value for that one, and we put it in here. And do the calculation. If that calculation is plus or minus 5% of that value, then our assumption is considered valid. So we need to do that calculation. Let's see, 0.1 subtract 3.16 exponent 3. Right? So that's 0.0968. 0.0968. Okay. And this one would be 2 times that value. .32 times 10 to the minus 3rd. Yep. 6.32 times 10 to the minus 3 molar. All right. Now let's put those values in here. This one goes in here squared. I've already got it in my calculator, so I'm going to square it. And then this one goes in the denominator. So that's 4.12 times 10 to the minus 4th. So is that within 5%? Well, you take, what's the difference? 0.12 divided by 4 times 100. That's 3%. So this is 3% off. That's considered valid. Okay, so let's see if that's the answer that they got. 0.097 rounded off. So there you go. But I introduced that 5% rule just to be sure that the assumption that we made down here is valid. Now, if you want to get closer, all you have to do is take this expression right here and plug in that value right there. For the one, well, no, not that value, this value, this x value. Take that x, put it right there, and then recalculate, solve for this x. And you'll get a new x value, which will be closer to the true value and will, in the final analysis, be much, much less than 5%. It'll probably be less than 1% by quite a margin. So if you want to get really close, then you can do that estimation. Then you can also do successive approximations, just like that. Okay, now to Le Chatelier's principle. That experiment should be coming up pretty soon, because I timed them so that the labs would coincide with the lectures. So what's Le Chatelier's principle? I mentioned it at the very beginning of the class when we were talking about adding components and taking away components at equilibrium. Le Chatelier just put that into a statement. And he said, if the system is at equilibrium and you do anything to disturb that equilibrium, the system will react. And it will react in such a way as to reduce the change that you've imposed. Okay? I think the fancy word is mitigate. It mitigates the disturbance. Anything that disturbs the equilibrium. So if you do something that doesn't disturb the equilibrium, then Le Chatelier's principle is moot. I mean, you don't need it. Only things that disturb the equilibrium. All right, so let's see. Get rid of this right here. Okay. Like what? What could we do to disturb an equilibrium? Well, you could add or subtract components, right? It's easier with aqueous solutions to add than it is to subtract. But gaseous reactions, it's fairly simple to extract components from that. But adding components, changing the concentration of any one of the components will disturb the equilibrium. And the equilibrium will respond by shifting toward the direction where you subtract or shifting away from the side where you add. Right? So if we look at our generic again, look at our generic again. If we're at equilibrium and we add C, then we're going to shift back this way. Or if we add B, we're going to shift that way until equilibrium is reestablished and the concentrations placed into the law of mass action for that reaction give us the K value. So that's concentration. What about temperature? What if you change the temperature? Well, we know if we change the temperature that the rate law changes, right? Because we've increased the kinetic energy of the reactants and the products, so the rate is going to change, which means the rate in one direction might change different than the rate in the other direction, so it would have to adjust rates until they're equal again. So how do we make that prediction with an equation? Well, the way I look at it is, if the reaction is endothermic, then you look at heat as a reactant. So if you put heat into the reaction to get products, that's endothermic. So now, if you increase the temperature, what are you doing? You're adding heat. So if you add heat to an endothermic reaction, it's going toward products. See that? Just make heat one of the reactants. But if it's an exothermic reaction, you're going to get heat out on the product side. In that case, when you add heat or raise the temperature of this reaction, you're going to be adding that term, and it drives the reaction back toward the reactants. Okay, that's the best way I know of to determine the effect of temperature on a reaction. Okay, how about pressure? Well, if all of your reactants are aqueous, in the aqueous phase, or you have any solids or pure liquids, pressure is not going to affect them, right? Pressure has almost, well, for all intents and purposes, has no effect on the concentration of solid or liquid, or concentrations in liquid as well, aqueous. So really, pressure has an effect only on reactions that involve gases. So if you do have a gas in your reaction, then pressure can make an impact on the reaction. Okay, so think about it this way. If you have a reaction vessel, and you've got reactants and products in here together, and they're gases, suppose all the reactants combined represent 2 moles. And the balanced equation says when that reaction goes, it's going to make 4 moles of product. Total gases, 4 moles of gas. Okay, so on the reactant side you have 2. Let's use this as an example. 1 and 1, that's 2 moles of reactants. On this side we have 2 and 2. So I have 4 moles of product. Okay, now if you increase the pressure, which is going to do what? The system is at equilibrium. So if you increase the pressure, you're going to squeeze into a smaller volume, right? So how's the system going to alleviate that added pressure? Well, remember, pressure and volume are inversely related. So if you decrease the volume, in order to alleviate that pressure, you've got to decrease the pressure too. As the pressure increases, the volume would have to decrease, right? P times V equals constant. So if we increase this one, that one has to decrease. So how do you decrease the volume? Well, maybe you don't. Maybe what you do is you make fewer molecules in that volume space. And based on this one, then by decreasing this amount, you alleviate the pressure. So the short version is, if you increase the pressure, the system is going to respond to produce less in total moles, which means if you increase the pressure on this one, it's going to shift to the left to go from high numbers of moles to low numbers of moles. If you decrease the pressure and expand the volume, then it's going to go the other direction. It's going to fill the space with extra gas. And remember, that only works with gases, right? Liquids, aqueous solutions, solids, doesn't matter. So if we wrote the reaction the other way, if we had two over here and one each over there, it'd be just the opposite, right? So in order to make a prediction, you got to have the balanced equation with the gases and their coefficients in order to make the prediction. If you just say increase the pressure, what happens? Shift to the right. That means absolutely nothing unless you have the balanced equation. Okay. So for that reason, when you do the lab for Le Chatelier, if you say shift to the right or shift to the left, you better be referencing an equation. If you don't reference an equation, then I don't know which direction you're talking about. Now, if the question itself says, this is the equation, which way will it go, left or right? Well, that's fair because the equation's already given. But if you've got a description of an equilibrium situation and you're saying, trying to explain what happened, shift to the right, and there's no equation to go by, that could mean anything. Yeah, it has no meaning. In other words, you missed the question. You lost the points. So you better put in that description a balanced equation before you start saying left or right. Okay. So those are the, and pressure also references changes in volume, right? If you change the volume, you're going to change the pressure based on Boyle's law. So here we have an example. This is not going to play because it's written in a language that's no longer supported, right? A flash video. But what happens is this iron, that previous reaction we studied, iron looks yellow, thiocyanate is clear. When you put them together, you get a red substance. Oh, that one's going to do it too. Right. Okay. So these videos, I need to remove these videos because they can just be confusing if they're not allowed to play out. Right. It's not going to work. All right. So that's the end. And I'll make myself a note. I've got to replace those videos with something if I want an explanation, in other words. Okay. So that takes care of equilibrium the introduction of the material. And now what you've got to do is work those review problems in the review document so that we can come back next Friday and discuss them and do a bona fide review so that you'll be ready for the exam in the following week. Now this review is going to come, let's see, let me check the list. I may have already done this. I'm just short on memory. Right, so we're going to have, today we did the introduction, review on the 5th of March. Oh, good. You have an exam on the 12th of March, and the midterm grades are due that following week. So that'll give you 3 exam grades, along with the labs that I will have graded by then, to constitute your midterm grade. That's good. It's better when you have a mix of labs and exams to go by. It's an honest estimation of your progress in the course. Okay, we're done for today. And I was all alone today. So my class, I guess those that are left are going to view the video. And we'll stop it right now.